2.1 number 7. All right. So it gives us a table of values. And then asks us to calculate the average velocity over a bunch of intervals, right? So let me just do one of these intervals, and after that I think like they're kind of all the same and it should be fine. Does that feel okay? So the first interval I think is like 1 to 3. So what I'm going to do is I'll do oh, sure. You want to do 2 and 4? It's because I'm looking at the 7th edition book now, and you're looking at the 8th, which is fine. 2 and 4, sure. So what I'll do is from my table, I'm going to pull the displacement for 4, which in my book says 17.7, and the displacement for 1, which is 5.1, and divide it by the difference in the times. Basically, we're just calculating the slope. And whatever that comes out to be is the answer. That's done. Okay with that, Mackenzie? So velocity is just displacement divided by time, right? Like meters per second. So I'm just going to look at how much distance was covered and divide it by the time it took to cover it. And that'll be my average velocity. It's basically just a slope where I think about the displacements as my y coordinate and the times as my x coordinate. Does that feel okay?
Yes.
Okay. And then you would do that for each of the 4 intervals that you're given, which is fine. Then it says, use the graph of s as a function of t to estimate the instantaneous velocity when t is equal to 3. So what I would do for this, there's a couple of different approaches you could make. I'll tell you what I think would be the obvious one and the one I assume that the authors would intend that you use, is I'm going to just take the 2 average velocities that are closest to 3 and then take the average of those 2 results. So like I would assume that we're supposed to be taking the average velocity from like 2 to 3 and then the average velocity from 3 to 4 and then just take the average of those 2 numbers. Will give us a pretty decent estimate for the instantaneous slope at 3. So I'm going from 2 to 3, and then from 3 to 4, and I'll take the average of those 2, and that'll probably be pretty close to the slope.
So wait, oh, I see what you did. You take the slope, and then you add by the other slope, and you divide by 2.
Yeah, just take the average of the 2.
I got it.
Alternatively, Mackenzie, you could have gotten pretty fancy with this. You could have built a scatter plot on your calculator, fit a regression equation to that, and then used the techniques that we did to like find an instantaneous slope where you have an equation for a function. You could have done that where you look at like 2.999 and 3.001 and kind of see what's going on there. You could do that. That would be okay. And the other way you could have done it is just to sketch the scatter plot out and just kind of like eyeball what a tangent line would have looked like and then estimate the slope of that line from your picture. That's not an unreasonable thing to do either. Those are really, at this point, the 3 ways that you could have gone about approaching that, though. I think that likely because of the table that they were given and the fact you did all these average velocities for part A, I assume that this is kind of what they would want you to do for part B. Does that feel okay, though? Okay. You're welcome. I thought I saw your hand. I can speak. Sure. So 9 says the point 1, 0 lies on the curve of sine of 10 pi over x. If q is the point x comma sine of 10 pi over x, find the slope of the secant line PQ, correct to 4 decimal places for a whole mess of values, and then it says, do these slopes appear to be approaching a limit? Okay? So we're looking at, basically, we're wanting to look at x equals 1, right? That's the point that we're interested in, or where the slope is, that the slope at that value of x. So all I'm going to do is let's do this all in my calculator. This will be the easiest way to do it. It'll be the least annoying way to do it anyways. So I'm going to go ahead and type in the function that they gave me into my calculator. So sine, and then I'll do the fraction 10 pi over x. Okay, cool there. All right, I'm going to go ahead and press enter, and then it says that we want to find the slope of the secant line. So one of the points on my secant line is the point P, 0, 1. The other point is going to be from the function. So I'll do, in this case, y1 of, and the first number they want me to use is 2, and then minus the y coordinate for P is 0 over 2 minus the x coordinate for P, which was v1. So that's my first value. And the next one it says to do is 1.5. So there's my next y coordinate. So I just went back and edited to make and turn the 2's into 1.5s. And I'm just going to kind of keep doing this. So I think 1.4 is next. Oh boy, what mode am I in? Ah, good call, guys. Okay, try that again. Oh boy, Mr. Kulik. Okay. So there's 0 for the first one. Yep. There's 1. Oh, that's pi over 2, right? You recognize that? Or I think it's pi over 2. That looks right. Maybe it's not. Then change that to 1.4. You guys liking anything going on here? Doesn't look like much of a pattern to me, does it? Then we go to 1.3. That's pretty yucks. I do 1.2. And I'm just going to keep updating this formula that I've typed in. Do you see where we're going with this, Mia? At this point right now, I'm pretty convinced that this is not approaching any kind of stable value, right? We've been jumping around from positives to negatives each time we're going. So if I scroll by this, yeah, I'm not looking, this is not looking good to me. Like, we keep getting further away, it seems like, from 0. This appears, and I would continue doing this for the other values, but like, I think at this point it's fair to say that this looks like the slope here is divergent. The limit doesn't, or the slope doesn't exist here. Oh, do the slopes appear to be approaching a limit? That's the question they ask. I would say no, right? Use the graph of the curve to explain why the slopes of the secant line in part A are not close to the slope of the tangent line at P. So let's go and look at the graph of this. So we'll just go from 2 to 0. That's basically what we had surrounding that. And I don't know, -10 to 10 is probably okay. Oh, what did I do? Oh, that's 0 to 2, Mr. Gulick. So my explanation would be that, let's do this, because these were, oops. I'd always I get so motion sick when I do that, and it just jumps to the other side of the screen. It's like, ooh. So I put the little tick marks in, and actually let's do this also. Oh, come on now. Okay, come on, you stupid thing. And let's do this also. So 1 is right here. So if I look at these, the issue is that at every 10th, it looks like we're hitting up the maximum or minimum in the graph, which is not really helping me settle down to the y value, because we're just hitting the amplitudes are the points that I'm picking. It says, by choosing appropriate secant lines, estimate the slope at P. So all of the stuff I would do would be between 0.1 and 0.9 is all the stuff I would pick would be right close in there. So I think if we do the same thing, but we start at 0.1 and then we go to 0.01.
You just choose that because X is
1? Well, we're looking for the slope at 1, right? Because it wants I'm talking about the secant line PQ, where Q is the point that's getting closer.
Right.
We just started kind of too far away to be, or we didn't use a fine enough grain,
Right.
when we were looking at getting it closer and closer.
Okay.
And I think if we do that, we might get some better luck out of that. Because because it's asking us the slope of the tangent line at P, right? We're not asking what the value of the function is at P. We know it's 0. It tells us the point P0, or P is 1, 0, right? So we're looking for the slope there. That is...
What was the answer for?
So it's just an explanation. So if we looked at the values that we were getting, they were at the amplitudes when we were evaluating that thing. So they just weren't on. If this is, I think this spot right here is 1, 0. Let's do this. This'll help. So that's where, see the brick where that's 1, 0. So the problem is the points that we were picking were here, and then here, and then here. They weren't close enough.
Right.
So that's why we were getting funky values. What we just need to do is pick our points for Q that are just much, much, much closer to 1, 0. And if you do that, then you should see see everything coming down to what we're looking for.
We're just looking for a slope.
And we're just looking for a slope. And if you look at that, that's pretty steeply negative, right? We'd expect the slope to be a negative number, and probably that's pretty darn steep. That's probably 30, 40, 50, like very
Right.
quite steep.
So you can just like kind of
Um,
over to the left of that on that and go to the right and then like kind of find axes, the slope intercept.
well, you're just like picking fine enough grains.
Okay.
And
But I mean, like if you pick one to like the left of that, just a little bit, and then to the one to the right of that, just a little bit, and you subtract the two. I mean, you use like the slope intercept form that way.
slope
No,
intercept.
no. Sorry. Like,
Just like I was doing.
yeah, just like you're
Just like I was doing here.
Y1 and then
Yeah.
correct. Yeah, that's what I meant.
Yeah. So if I keep going, like we just have to, like you have to really do a fine grain.
Right.
And it looks like we're heading to like negative 31 point something, 0.3, 0.4, something in that ballpark.
Yeah. Okay.
You want to check the other side also, but it's going to be fine. We can tell by looking at the
Right.
picture that clearly this limit exists because the two slopes should match up.
So do you keep just going?
But-
does it matter how far you get, or like you just need it far?
No, I mean, we're estimating. So like I would say if you're within, a tenth or two of the actual value,
Okay.
I would say that's close enough, right? So the back of the book's answer is negative 31.4. I would say if you're within like 2/10 of that either way,
Okay.
I would say that's a reasonable enough estimate.
Okay.
Anywhere from negative 32 or 31.2 to negative 31.6, I would say, yeah, for an
So,
estimate,
as
that's
long
good
as
enough.
it's close enough, you just plug it in the calculator and it should be fine.
Well, I'm just doing slopes. I'm just getting really, really close to 1-0,
Gotcha.
and that matches up with what we're seeing, right? Remember, this is 0, this is 1, so that is pretty darn steep, right? Like that's a pretty steep negative slope. So
Right.
negative 31 for a slope
Makes
is
sense.
that matches what I'm seeing, right? Does that help?
Yes.
Sure. Be cool with questions here. I didn't write down a lot of 9 here, but because it was all like I'm just using my calculator. I'm not writing all that stuff. That is a lot of stuff. Mackenzie. From
They're the same on both books. No. Or, yeah.
oh yeah, I was like, there is no 11 in chapter section 2.1. Okay. So here we're given a piecewise defined function. Do you know what that means? Okay, well let's talk about how we would go about even getting a picture of this, right? Does that, Mackenzie, does this match what you have? Okay. And it's asking sketch a graph and then determine the values of A for which the limit exists, right? Okay. All right. So what this is saying is it's giving us, on the right here, it's giving us the domain, and then how that function behaves for that part of the domain. Does that feel okay?
Yeah.
So here's -1. So when I plug -1 into 1 plus x, I get 0, right? But -1 is not included in the domain, so I'm going to use an open circle there. Everybody's okay with that? And then I'll plug in, say, -2. 1 plus -2 is -1. So I'll have like a point here. And since I know that that part of the graph is linear, 2 points is enough to draw that part of the graph. So far, so good? Okay. Let's go to the green part now. And I'm going to use 3 different colors here just so it's super clear like what part corresponds to what. Is that okay? It's all the same graph, but I'm just going to color code it in case you go back and look at it. So I'm going to, again, to graph a quadratic, I need the vertex and then a point or 2 on either side of the vertex. What's the vertex of the parabola defined by x squared? 0, 0, right? That should be easy. If I plug -1 in for x squared, I get 1. And -1 is in the domain, so that's going to get a filled in circle. We said 0, 0 was the vertex. And if I plug the other end in, 1 squared is 1, but notice that 1 isn't in the domain for that part of the function, so I'm going to use an open circle there. So I'll draw the rest of my parabola. Sergio?
For the yellow one, why would -1 be in the domain? If
'Cause
it's like less than or
it's not in the domain,
right.
right? So that's why I used the open circle there on the graph in red.
That's -2. I'm a little bit slow. It's okay. All right.
Okay. We're good?
Yeah.
Counting, it's hard, right?
That's hard for me.
All right. We'll move on to the last section now. Again, I noticed that the last section of the graph is linear. So again, all I need is 2 points. I'm going to plug in the point 1 because that's in my domain. 2 minus 1 is 1. So we have a point here at 1, 1. And then if I plug in 2, 2 minus 2 is 0. And I have that. Is everybody okay with how I constructed the graph there?
So we're finding the y values by plugging in the x values?
Yeah. So I'm making just like an XY table. For the red, I did -2 and -1, which gave me -1 and 0. And then for the blue, I did -1, 0, and 1. And then for the green, we plugged in 1 and 2, which gave me 1 and 0. Does that feel okay? All right, so if I look at this graph, where is the only place where we're going to have an issue with the limit? At -1, right? That'll be an issue. There's actually one other place. I think at +1 we're going to have an issue also. Why would that be? If I'm going on looking at the left-hand limit, that's going to have a positive slope to it, right? Because that part's increasing. But if I look at the right-hand limit, that's going to have a negative slope on it. Don't think those are going to agree. You guys buy that?
Do you like the red line again?
The red line?
Yeah.
Yeah. So I picked the points, the x values that were less than -1. So I picked -2 and -1. So when I plugged -2 in, 1 plus -2 is -1. So I plotted 2, -1. And then when I plug -1 in, 1 plus -1 is 0. So I have the point -1, 0. But notice that -1 is not in the domain for this function. So instead of putting like a filled in circle, I'm going to have an open circle.
Just for that. Just for that concept.
Yes.
Why not for like the other one?
The green one?
No. Like the other little point in the red.
Because -2 is less than -1, right? If I plug -2 in for x, that's less than -1, so that's in the domain. That's why it gets a filled in.
Oh, but negative, right.
But -1 is not less than -1, so it has to get an open circle.
Why did you plug in negative?
Because I need to know where that graph stops at, right? It's 2 points, or it's a straight line, so all I need is 2 points, but it's not going to be a straight line forever in that direction. It stops being a straight line at -1, so I need to know where it stops being a straight line at. So I need to know, like, where's that open circle, like, where's the end of this line.
Okay.
Does that
Yeah.
track?
Yeah.
You just got -1 from itself, the long equation.
Yeah, when I'm looking at a piecewise function, I'm always going to be using the ends of the domain as points in my piecewise function because I need to know where to stop that piece, right? You might need some other stuff in the middle, or you might not, but you have to absolutely have the endpoints because you need to know, like, where does it stop doing what it's doing. Did that? And Mackenzie, I misspoke here because I misread the directions. It's asking about the limit as x approaches a of f of x.
Yeah.
So this is okay. I thought we were looking at the slope of the tangent line. I didn't read the question well. So that point is fine. So your answer is all values of a except -1.
Why?
This.
Oh.
What? No, +1's okay. I misread the question when I explained that earlier. I was talking about the slope. I thought we were talking about the slope of the function. It's just asking for the limit as x approaches a of f, right? If you look at the green, that's going to +1. If you look at the blue, that's going to +1. That's fine. If we're talking about the slope of the function, then that piece would be an issue.
Okay, they're on the same, or they have the same. The one's like has -1 and it doesn't.
Yeah, so let's write it down, right? So the limit as x approaches -1 from the left is 0. The limit as x approaches -1 from the right is 1. That limit doesn't exist at 1 or -1, right?
Yes.
If I
Don't match.
because they don't match, exactly. If I did the same thing at +1, the limit as x approaches 1 from the right is 1, and the limit as x approaches 1 from the left is also 1, that limit exists, right?
What's going on with green? Oh, wait, never mind, sorry, I got confused, but highlighted and, like markers, you know?
This is the highlighted green.
Yeah.
Is that limit.
Like up there, I was looking.
Oh, okay.
And then I just confused myself with the table green and then the.
I gotcha.
highlighted green, so.
Gotcha. Okay. Does that track, Mackenzie?
Yeah, that.
All right. Let's finish up this this section 2-3. Okay. So, last thing we had done in 2-3 is we had talked about these limit laws, right? And we made the observation that if you have a polynomial rational function you're taking the limit of, you can try direct substitution as a way to evaluate the limit. Let's look at a non-numeric example that would that we can use these limit laws on, though. Okay. Oops. And this is going to be f of x. Okay, so let's say you're given the graph that I just provided, and we're asked to find the limit as x approaches -2 of f of x plus g of x. I can use my limit laws to think about this just as the limit as x approaches -2 of f of x plus the limit as x approaches -2 of g of x. Everybody cool with that? Okay. And now all I have to do is go to the graph to evaluate. So at -2, f of x, the limit as x approaches -2 of f of x is one. And the limit as x approaches -2 for g is -1. So that's 0.
Wait, I have a question.
Wait.
Sure.
So the limit there is the y value, not the x. 'Cause how would you get 1 for that?
So this is the point -1, 1,
Right.
right? This is the point -2, 1.
Right.
This is the point -2, -1. So as x is approaching -2, here the y is approaching 1. And here as x approaches -2, y is approaching -1.
Okay, yeah, that's pretty straightforward.
So I'm just looking at the picture and reading it from the picture, right? Yes, Victoria.
Like, did you do, like, is -1 for the, GX?
G of x?
Yeah. But why don't you use like the point that doesn't have a line?
Why didn't I use the point that doesn't?
Why do you use-
Just talk about the point -2.
Yeah, -2, 2.
Okay, why did I ignore that point?
Yeah,
Because I can't use direct substitution to evaluate the limit of f of x because f of x is not either a polynomial or a rational function. I don't know what it is.
okay.
So I could not use direct substitution here. And in fact, because it's discontinuous, right, we have this removable discontinuity going on, I know for sure that it's not a polynomial or rational function.
Okay, another question. Why did you, for f of x, you have used -1 for 1?
For f of x.
Like for f of x, you said that it was 1. Could you have used -1?
So f of x, we're traveling along this curve, getting close to -1,
Oh, f of
right?
x is blue. I did not see that. Yeah, I got it now.
Okay,
Okay.
cool. Okay. We're doing some more, just using the same picture. So Robbie, you got a question or are you good? You guys okay?
Yeah.
Okay. No, if you got a question, like ask. It's no big deal. That's why we're doing them, right? You guys haven't done this before. It's new to everybody. All right, let's look at the limit as x approaches 1 of f of x times g of x. We can use our limit laws to do the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. That okay? So now I go to my graph. I go for f of x, and I go look at what's happening as x approaches 1. The limit as x approaches 1 for f of x is 2. That okay? Just read it right off the chart. And I'll do the same thing now for g of x. What do you notice here? So what should I say?
Divided by
Just
It
two
doesn't
negative,
exist,
two
it's
values.
just 2 points.
Yeah.
Because it's not meeting at the same value.
Right, okay.
Right? From the left and the right, they're not meeting at the same value. That limit cannot exist.
Can you go over again why it's 2? Like, I get where you're pulling it off the graph.
I'm just traveling along. What is the y coordinate turning into?
Oh, that.
2. Right? Because that's the point at x equals 1.
Whoa, yep, okay, I got it. Yeah. I was looking at red.
Oh. Guess I should have done red as g of x and blue as f of x, or written the f of x one first or something. I think I threw everybody off on that.
So, yeah, whatever I can guess.
Yeah.
Oh, and now I understand the one up. I didn't put -2, that's why. That's why I was a little confused, because I was looking at 2 the entire time. So,
Yeah. That's what it must have done. Okay.
because they're not intersecting, you can't have anything.
What?
For B, G of X, because they're not touching.
Well, it's because they don't, the left-hand limit and the right-hand limit don't match.
Yeah, they're different. That's it.
All right. Let's skip that other example because whatever I wrote down doesn't make any sense anymore. So, seems like a good thing to skip. All right. So, simple little proposition here. If f of x is equal to g of x, when x is not equal to a, so at every point other than a, these two functions are equal. What should we be able to say about their limits? They should have the same limit, provided what? What little caveat do we have to add in there? The limits have to exist, right? Because you can't say does not exist equals does not exist. I know. All right. Let's take a mimit, or a mimit. What is a mimit? Let's go and do some more examples here of some algebraic limits. So let's say we just want to evaluate. And we're going to do these things all algebraically, just to get you an idea of what's going on. Can I use direct substitution on this as it's currently written?
No,
No, why not?
because your offspring is
Because I'll have a 0 in the denominator, right?
Oh, yeah, that's right.
Everybody's okay with that? So what I'm going to do first is I'm going to see if there's any simplifying that I can do to try to get that h out of the denominator. Everybody's okay with that?
Yeah.
Any ideas of what I might want to start by trying?
Multiplying by h.
Well, that's still going to give me h's in the denominator. Sophia, what were you going to say? Yeah, let's FOIL that quantity out, right? 3 plus h squared, you can FOIL that out. So you get 9 plus 6h plus h squared.
Oh, I see.
Everybody's okay with that? What do you notice we can do now that we've done that?
Cross it out.
The 9s are going to cancel, right? I have a plus 9 and a minus 9. And then if I factor an h out of the numerator, I can reduce this. Is everybody okay there? And now we can use direct substitution, and that's just 6. Neato, right? Neato. So even though this was a rational function, the problem was we were trying to use direct substitution on a value that's not inside the domain. That's why we couldn't use the direct substitution piece, because we would get a 0 divisor. Mackenzie? Well, 6 plus 0 is 6, right?
Oh, so you look at the, okay.
Huh?
Okay.
Is that okay? Okay.
Can you use direct substitution if the number's not 0?
You can use direct substitution if the value you're plugging in is in the domain of the function. But 0 is not in the domain of that starting function, right? Because if I plug 0 into that, I get undefined. So I couldn't use direct substitution to start. I had to do something else. Let's look.
When you did get h out of the denominator.
What?
How do you know that though? Is it just
Because when I looked immediately, if I tried to plug 0 in,
right?
I get undefined. Can't use direct substitution to get undefined, right? Because now you're plugging in something that's not in the domain of the function.
Right.
So I had to do something else. Does that feel good?
Yeah.
Okay, let's look at a couple more. I got a couple more to do. These little tricks that I'm showing you, they are pretty canonical tricks. These are things that frequently come up. So like just doing some general simplifying and trying to reduce is a good first option. Can I use direct substitution on this? No, why not? You get a 0 denominator, right? So 0 is not in the domain of the function, so it can't do that. So we're going to want to do some kind of simplification to try to cancel that t squared out of the denominator. Any ideas of what I would want to do? Well, how are you going to do that? You can't break a square root across an addition symbol. Where it's not an equation, there's not two sides to square. Nope. You definitely can't do that. Like if I take 1/2 and I square the numerator and square the denominator, I don't get 1/2 back, I get 1/4. So not okay to do that. Multiply the top and bottom both by not t squared, not negative t squared.
1 over t.
Not 1 over t.
T over 1.
Not t over 1.
Square root t squared plus 9 minus 3, plus 3.
Why would I?
Oh, because it's so. What is that? I know
What is that I'm doing? Multiplying by the conjugate. Conjugate is the name.
I got it. There we go.
Why is that? Why is that going to be helpful?
Because it gets rid of
Cancels
the on the
out.
bottom.
Remember that a plus b times a minus b is equal to a squared minus b squared? You remember this factoring pattern from Algebra 2?
Yeah.
That's the difference of two squares, right? That's what I'm doing here in the numerator, is it not? I have a minus b and a plus b. Everybody agree? You can see it? So when I multiply those together, I'm going to get t squared, or the square root of t squared plus 9 squared minus 3 squared. And why is that a good deal? Oh my goodness, guys, I made a big mistake here. Hold on 1 second. This is like the calc teacher's biggest pet peeve. I forgot to write limit there. That is something that if you make that mistake on like the AP test, you will not get marks, full marks for that. That would be something that they would mark down and that kind of a thing.
With Mr. Cooling.
Well, you're saying that a limit is equal to an equation. Nope. Yes. You got to make sure you're carrying them over, though. That is something that I will be picky about, and the person grading the AP exam would be picky about. I know, but here's the thing. I'm telling you right now.
Right.
So that equation above, like the 6, would you use that for the 6 or no?
Mackenzie, I'm sorry. No, the 6 is done.
Okay,
We've evaluated the limit,
all right,
and it's just equal to 6. That's what you're asking?
yes.
Good. Yes, that is fine. Okay. So why is that multiplying by the conjugate great? It's going to cancel the radical in the numerator. Right? No more radical there. The squared cancels the square root. So I have t squared plus 9 and then minus 9 over t squared times the quantity, square root t squared plus 9 plus 3. Everybody's cool with that? What do you notice? Plus 9 minus 9 cancels out. And then the t squareds can reduce. What did we just do? We got the t squared out of the denominator. That was the whole problem in the beginning, right? If I plug 0 in now, do I get undefined?
Yeah.
No way, Jose.
Really?
Yeah, I'm good to go. So notice that the limit has gone away
Right.
because I've plugged 0 in, and my answer is 1/6. Everybody feel good with that? So these two tricks that you've just seen, like just doing some simplifying and reducing or multiplying by a conjugate, are really common, like limit tricks to take something that you can't use direct substitution on and turn it into something you can use direct substitution on. These will come up over and over and over again throughout this chapter, okay? So these two tricks are great ones to remember. We'll talk about some others as they go, because we'll see some more, but these two are pretty classic examples of good tricks to take something that we couldn't do something easy with and turn it into something we can do easy, which is nice. All right. what I want to talk about next is called the squeeze theorem. So this is something that I have frequently seen AP questions regarding. So this is a good theorem that this is something you'll want to remember. It's something we'll want to be able to use. And what the squeeze theorem is useful for is, let's say we have a limit that we can't use direct substitution on, and there's not a way to simplify it so that we can use direct substitution on. The squeeze theorem is an effective tool to still evaluate that limit. Okay? So what the squeeze theorem says, it says that if I have three functions, f of x, g of x, and h of x, where f of x is a lower bound on g, and h is an upper bound on g. I'll draw a picture and show you exactly what I mean by that in just a second, okay? When x is near a, and then I'll say except possibly at a, and the limit as x approaches a of f of x equals the limit as x approaches a of h of x, that are both equal to x, or equal to L, some number L, then the limit as x approaches a of g of x is also equal to L. So what we're doing if I draw a picture here, let's say that this is the value a, and let's say that we have some function here. This will be my h of x, and some other function here. This would be my f of x. Then we could have some like cuckoo crazy function here. Oops, be a little bit more careful there. That's my g of x. That if those two functions are bounding g of x and their limits exist, then g's limit exists and it has the same limit. That's basically what this is saying. Let's do an example where we can apply this. Actually, I'm going to write this as show and give the answer. All right. First thing I want to point out, if I use direct substitution, does this work? No, why not? You'd end up with a 0 in the denominator. Because of that, can I use the limit laws to break this thing up into like a product of two limits? No. The limit doesn't exist you can't use the limit laws. So if I tried to plug this in, right, the limit's not going to exist, right? So we can't use the limit laws to break it up. So we're going to have to do, this is why I'm going to have to do the squeeze theorem. Okay? There's no simplifying that I can do here. There's no tricky algebra thing that I can do to like cancel the x out in the denominator of the sign, because I can't even get anything into the sine function. There's no way to move anything in. You know what I mean? So what I want to do is I want to find a function that bounds x squared sine of 1 over x from above and from below. So here is going to be the trick. What do we know about the function sine of x? If you graph the sine of x, what values are bounded by the sine of x? What's the smallest value that can come out of sine of x?
Smallest value?
Yeah. This is just a unit circle.
-1.
-1. And the biggest value is
1.
+1, right? So we know this.
How do we know this?
I plugged it in my calculator.
This is trigonometry from last year. So the unit circle has, the biggest value on the unit circle is +1. The smallest value is -1. So those are the biggest and smallest values that sine can take. Is that okay? So if this is true for sine of x, it's also got to be true for sine of 1 over x, right? Because it doesn't matter what was in there. The only thing coming out of sine, the smallest thing is -1, the biggest thing is +1. Doesn't matter what the angle was, right? Whether you want to call it x or 1 over x, whatever. Everybody's okay with that?
Yep.
Everybody's cool? Still doing good? Now I'm going to multiply all sides of this inequality by something. What should I multiply by? Nope. Multiply by x squared. Why x squared?
Oh, because you're multiplying the sine of 1 over x by x squared.
Because that'll give me the original function that I am trying to take the limit of. Right? Everybody's cool? So what do I have here? I have my f of x, and I have my h of x. Can I evaluate the limits of f of x and h of x really easily? Yes! Those guys are polynomials. So I would say the limit as x approaches 0 of -x squared, that's just going to be 0 squared or 0. And the limit as x approaches 0 of +x squared is equal to 0 squared or 0. So I can say by the squeeze theorem, the limit as x approaches 0 of x squared sine of 1 over x is also equal to 0. This step is the most difficult step, is to construct your values for f of x and h of x, to find the two functions that bound it. Now, for you guys, you'll see trig functions almost always kind of involved with this, and remembering your bounds for your trig functions will become quite helpful in that regard.
So that's the answer.
That's the answer. Well, it's like a proof question, right? It says like show that this limit is equal to 0.
Oh,
So we knew what the answer was going to be.
right.
We just had to show it. So I showed how I found my two functions, my f of x and h of x, and then I evaluated their limits and applied the squeeze theorem.
Okay.
All right. I'm gonna write down. Actually, can I just come back and write in the homework for 2-3, update it here in a later today or something when I get a chance to look at things, because the things aren't gonna match, and I'm just gonna end up like assigning you some terrible question that's like just not at all one that I meant to be picking, and then it's gonna be a whole thing, and you guys are gonna get mad about it.
Tell me it was gonna be a Saturday, Sunday problem.
That's true, Sergio. Now, we took more time than I thought we were going to today to do this, and that's okay. What I'm going to ask for you guys to do then tonight is to go to, okay, let's start at the beginning. Right? Mr. Kulik, start at the beginning. So, from the links page, I'm going to click the My AP link. We all did this. Oh, I pressed the wrong thing. We all did this before and signed up and registered for the class. So you'll do your sign-in stuff. And down here, we should have the like an assignments thing. I'll have a little link to say like assignments or something. And I have made a 10-question multiple choice. I think it's called a quiz. I think that's what they have to be called if the thing's going to grade them for me. Or maybe it's just called an assignment.
It was called a quiz.
It's called a quiz?
I think it's
Okay.
at Office 1.4.
Yeah, okay. So this is what I got for you guys. So this is just like the preview of what it's going to be. So these are just questions that are kind of covering the content we've done up through like 2, 3.5. So just like evaluating limits or calculating average velocities or instantaneous velocities using a table or a graph or, so just like kind of normal-ish stuff that we've been doing. Everybody's okay with that?
Yeah.
We have 10 minutes left, right? I think this thing saves your progress as you're going through. So if you wanted to start now, try to, bang through a couple. I think it's set to the questions to be in a random order. So everybody has the same 10 questions, but they're going to come up in not the same order for everybody. Which maybe in hindsight that was inconvenient to do, but and let's say that, like, again, let's say that we had said wanted to set some bands for this, right? Let's say 8 to 10 correct is 10 points. Let's say 6 to 7 is 9 points. Let's say 4 to 5 is 8 points. And let's say that 1 to 3 is 7 points. And finish is, so 0 points, but you finished, is a 6. And then nothing is 0.
Coach, if you got like, I did, yeah, I know. If you say like, I was gonna say, if you get like 0 points out of 10, you should get like 7, just because that's harder. Like if you pick, if they're all multiple choice, and you pick them randomly, you should be at least getting one of those.
I would say if it was true and false and you got all wrong, that would be something.
Right, okay.
But multiple choice, you have 75% chance of getting it wrong. That's a much better than 50-50.
Right. But, okay, so if it was, what I would say is like,
if it was like true and false, like 10 questions, and you got all of them wrong, you should get like a 9 for that. Just because like that's equally, you know what I mean? It's equal. Like you have to get them all
The
right.
probability of guessing that was
Yeah,
the same
right.
as probability of guessing them all right.
Yeah,
Yes.
exactly. That's what I'm saying. So like, we should do that. You know, if they were all true or falses. You know.
So that Michigan